Good evening, all.
Sir, good evening. Vinay sir,
Good evening, sir.
how are you, sir?
Sir, fine, sir. What about you?
Everything is okay, sir. Thank you so much. So, sir, can we start now?
Yes, sir. Sure.
Good
Yes.
evening, sir.
Good evening, everyone. So today is our seventh day of this FDP, Statistical Programming in R. Yesterday, we discussed about the discrete statistics. That means the measures of central tendency, mean, median, mode, and measures of position. That means quantiles. Today, we are starting our journey with measures of dispersion and measures of distribution. So let's start. As everyone is aware of, mean, median, and mode. Yesterday, we conducted a session for that, and we discussed that. Today, we will do some more exercise with this. Let me show you the screen of today's topic. Here it is. Measures of dispersion. As the name suggests, the measures of dispersion shows the scattering of the data. In research, we collect large amount of data from population, and depending on the sample size, we can find out the scattering of data with measures of dispersion. It tells the variation of the data from one another and gives a clear idea about the distribution of the data. So actually, it will show you how diverse the data is. The measure of dispersion shows the homogeneity or heterogeneity of the distribution of the observation. The most common variability of dispersion measures are: number one, range; number two, median absolute deviation, also called MAD in short form; then variance; then standard deviation. So let's start with the first one, and that is the range. The function yesterday I told you is about range. It will give you the maximum and minimum of the data. But what the range actually is in our statistics, the range describes the difference between largest and smallest data point in our data set. Means if you are having some minimum value in your data set and one another is maximum value, and their difference will be called the range. The bigger the range, the more is the spread of the data and vice versa. So if data range is higher, that means spread is larger. The range is minimum, then spread is lower. So range equals largest data value subtracted smallest data value. That will give you the range. Actually, this is the statistical range. But in R, we have studied range function that gives you maximum and minimum value of the given data, not the subtraction. So for that, we have created a program over here. Let's illustrate that. Here, our program to illustrate the range. Import the data using read.csv. This was the previous file that I was using in some previous classes. Right now, I am not having this, but we'll use cars data instead of this. Calculate the maximum and minimum of the range. How we can do in the programming? First, find max. That means maximum of the data. Here we are using the age data of my data frame. Then minimum of the data using the min function from my data and age. So column will be the age. We are finding the maximum and minimum, and we will find the range of the data for age. So the range will be max having the maximum value, min having the minimum value, and we will subtract that, and then we will print range. So what will be the output? The first one output is 32. But alternate method to get minimum and maximum, we already know R gives us the range function. If R is the range, then we will apply a range, then my data, and then the column on which we want to apply this function. Then we will print that and we'll get this value. You can see it will give you us 18 and 50, for example. And here is the, we have manually calculated with the max and min function. Range function gives you the maximum and minimum, and here is the difference, which is the actual range of the data. Here range is 32. That means you can find out how much data is spread. So let's do something on R console with our range and maximum minimum function. So let me show you the R console here. Here we are back with our R console, and you can see we have cars data, and we have two columns, speed and distance. Let's calculate the range. By using the minimum function, we will first find out the minimum. Minimum of, you can put the complete name because it is the variable name. The function will return minimum value in min variable. So minimum of what you want, cars data, and then dollar, then speed. First you have to find out the minimum of the speed, then you just find out maximum of the speed. So cars, dollar, and speed. Now you have two variables, minimum and maximum. You can print the value of these two. Here minimum is that and max is this one. Suppose you want to find out the range, then you can use range. Range is itself a function also, so it will suggest me that you can use the range function, but I am using range as variable. I'll take some value inside that. So it should be max minus minimum. Now I will print the range variable, and you can see it's very simple because 25 minus 4 equal to 21, but where there is a large amount of data, you can do in that manner. Similarly, we can calculate for distance also. But first, we'll see the range function that we will apply on this column. That means the speed column. And here you can see it will show me the range is from 4 to 25. So our function range returns two variables, minimum and maximum, where range is defined as the difference of these two. That means subtract minimum from maximum, that would be called the range. So this is how we can calculate the range in R. There are two different methods. Number one is using the range function that will show you the spread of the data with minimum and maximum value. And another one is the first find out maximum, then find out minimum, and then the spread as a difference of both these. This time we'll calculate some more data. Suppose this is our X data, X variable that we have created for our practical purpose. You can use directly maximum and minimum here. Maximum of, I am changing the variable. Max in max, now find out the maximum of X. This time in the minimum, find out minimum of X. Now you can print what is the maximum of my data, this time 87. Similarly, you can print minimum and you can find out that 3 is the minimum value. Now I can directly write print difference of maximum minus minimum. Here it is. So you can use for the vector variables in that manner. We can see the histogram of X once again. This to check the spread of data, we can use histogram function. Here it is. That is from minimum to maximum. We can see. Again, let's move to another topic. Here it is. And it is called median absolute deviation. The median absolute deviation is the static that gives the average distance of data points from the median. An acronym for this static is MAD. The image gives a visual deviation from the mean in the set of data. It can be from mean or it can be from median. Generally, it is taken from median. So suppose here it is the data. You can see the average is given, or you can also take the median. And after that, the spread, this blue color shows you the deviation. The deviation in the data. So how to calculate that? The formula is given by this. It is summation from 1 to nth term, where n is the total number of terms, and the absolute value of xi minus x bar, which is the median. And this summation is divided by the whole number of terms. Then it will give you the median absolute deviation. If you take x as mean, then it will call mean absolute deviation. Or if you take the median in x bar, then it is called median absolute deviation. That means both are the measures of central tendency, median and mean. You have to find out the deviation from that. The symbol here, you can see that these two bars where xi minus x bar is put. This symbol stands for absolute value. Means whenever you subtract, you have to take the positive value. no negative value will be taken into the account. The absolute value of a number is its positive value. So you have to take the difference, that means the deviation, only in positive. Suppose if x is 5 and you are taking first element as 1, then you have to subtract 1 minus xi, that is x bar is 5. 1 minus 5 will be minus 4, but you have to take the positive value, that means plus 4, that is the deviation. And all such summation of all such deviation divided by n is known as MAD, median or mean absolute deviation, depending on what x bar you are using. Either it is mean or it is median. We generally take median for MAD. Here, MAD function in R language is used to compute the median absolute deviation. Here is an R program to calculate median absolute deviation. Here, first we create the vector and we will call the med function on this. The output will be like this. So let's go to our R console and find out the median absolute deviation for the variables that are already available to us. Here comes our R console. As you know that x is there. Now to find out MAD and then bracket, you can say it is suggesting me the things. I'm just putting here x as input and it will give me the output as 32.6172. In general, the deviation of the values is in the form of how much? 32. In an average, it is 32. So you can also use this formula on the columns. That means MAD of cars, then dollar, then speed. Then we can press enter and you can find that the deviation of speed, that is median absolute deviation, is 5.9304. Similarly, we can find out it for the distance. Here it is. No, only dist variable is there. Here it is, 23.7216. That means it is telling me that the deviation is 23.72 in case of distance. In case of speed, it is 5.93 and so on. So you can also calculate, you import first your data into the R, and after importing the data into R console, you can use the calculations to find out the spread of the data with range, and another one is median. Let's go to another topic. Variance. You all know about variance. It is defined as an average squared deviation from the mean. Variance is always taken from mean. It is calculated by finding the difference between every data point and the average, which is also known as the mean, squaring them, adding all of them, and then dividing by the number of data points, total number of data present in our data set. And it is defined as sigma square is equal to summation of, yes, x minus mu, where mu is the mean, whole square divided by n. Means what you have to do for variance, first subtract each and every element and make the square of that, and sum all these squares and divide it the total number of terms. You will find the variance. This is the formula. Now, what is the program for that? R provides var function, that is variance, to find variance of the data. Here is the R program to calculate the variance. Now, calculating the variance, VAR my data and column name for which you want to calculate the variance, then print variance. There is the output. Now, this time we are going to R console to find out the variance of different data items we are already having. So here it is. I want to find out the variance of X. That is, we have already printed X over above few lines, you can see, and we will press enter. You can find out the variance is 700.6948. Similarly, we can find the variance for car, dollar, speed. Now, this time S was not there in cars. That's why it is giving me object car is not found. You must know, if you are getting that type of error, object not found, that means you are typing the wrong variable name. Here in cars, you can see speed. The variance of the speed is 27.95918. This time I am taking distance. So here variance is 664.0608. I hope this is clear. Then we'll go to another topic, and that is standard deviation. Here it is. Standard deviation is a measure used to quantify the amount of variation of a set of data values from its mean. A low standard deviation for a variable indicates that the data points tend to be close to its mean and vice versa. It is also used to examine if the data has a normal or nearly normal distribution. It is defined as the square root of the variance. So you already have taken variance, you can take the square root of that manually. So you can find the standard deviation. It is calculated by finding the mean, then subtract each number from the mean, which is also known as average, square all the result, adding all the values, and then divide by the number of terms, follow the square root. So this is how we calculate the standard deviation. In simple words, find out the variance and take the square root of that. That would be called the standard deviation. Here it is. You can see the formula. The standard deviation, this is equals to square root of sigma, that means summation of x minus mu whole square divided by n, where n is the number of terms, u is the mean. In R, SD function provides standard deviation. Here is the program. R program to illustrate the standard deviation, import the data, whatever data file you are having, you just import that. Then, for example, STD is the variable in which I am taking SD, that means the standard deviation. I will print and it will show me the result. So let's do it onto the R console. Here it is. Again, For visualizing purpose, I am again typing this. You can say this is my X, and SD. If I want to find out the standard deviation of X, I can use SD command, and here it is. You can also take the value for your calculation use into std variable, and then you can use sd of X. At this time, the value will be transferred to the variable std, and you can use std directly. And similarly, we can calculate for data frame also. The data you have imported to R, you can use them using this function in this manner. For example, SD, here we have inbuilt data set cars, then column name for which you want to calculate speed. This time it comes out 5.277644. And you know that we already having variance function for this, so we can confirm here. Here it is the square root of 27.95918. The square root of the variance is the standard deviation. So you can confirm that. Similarly, I can take SD, standard deviation for distance also. This time I am taking this variable. So it will show me that here it is 25.76938. To confirm this, that it is the square root of variance, I am also printing again the cars, then dollar, then dist, which is the variable. Here it is. So this is all about the variance and standard deviation. Let's go to another topic.
Sir, good evening.
Yes.
Uh, so there is no correlation between standard deviation and variance, right? One is same numerical number. Standard deviation is 25.76, whereas variance is 664.06. No correlation of the digits are numerical.
You can see that it is the square root of this. If you find out with calculator that variance, you just take the square root of variance, it will come out to be this much. There are two different terms named variance and standard deviation.
Okay.
So if you want to use variance in your calculation, then you have to use this formula. And if you directly want to calculate standard deviation, which is the square root of this value, you can use SD formula. Both are the very important terms in case of discrete statistics. That's why we have to learn both the functions. And I'm showing you that this value, when you square root, this will come out to be this. Okay, you can find out with calculator. If you type this value and you will take the square root, it would be this. That's why I have taken both the function to show you. Similarly, 27.95918, when you take the square root of this, it would be come out that much. And this is called variance, and square root of this variance is called standard deviation. R provides both the function, whichever you want to use in your calculation, you can use. That is okay. So most welcome. Then we'll come to other topic. I'll show you. And here are measures of distribution. The distribution shape of quantitative data may be symmetrical or asymmetrical. Now, what is the meaning of that? In another point, we have to clear it. Examples of symmetry and asymmetry are the normal distribution and skewed distribution. In symmetrical distribution, the two sides of the distribution are a mirror image of each other. That means there will be a shape like this. See my hands, there will be shape like this, where if you divide it by 2, you can find out that both are mirror images. So I will show you the image also a little bit later on. In statistics, skewness and kurtosis are the measures which tell about the shape of data distribution. These are normality tests to check the irregularity and asymmetry of the distribution. If you have collected sample data from any population, and you want to check it, then you can use the measures of distribution. Means you can check the distribution shape of data by plotting it either in the form of histogram. Bell-shaped curve will be there, and you can find out that mean values will be in the center of that bell-shaped curve. And if both three things coincide, then it is called the normal distribution, which is generally not seen in our practical cases when we collect the data. That means we can find nearly normal distribution because we are trying to relate the things. We are looking for the pattern in our research. That's why we will find new patterns by looking at the curves. So let me show you some examples. One by one we will take. To calculate skewness and ketosis in our language, moments package is required. Please note it down. We have to download and install moments package for skewness and ketosis. Now, what are these? Let's go to that. Skewness. Skewness is the statistical numerical method to measure the asymmetry of the distribution for data set. It will show you whether the shape is perfectly bell-shaped or it is something different. So skewness will show you the asymmetry of the distribution. It tells about the position of the majority of data values in the distribution around the mean value. It shows you the distribution around the mean value. The skewness value can be positive, negative, or undefined. It may be positive, negative, or undefined. In a perfectly symmetrical distribution, the mean, median, and the mode, what I was discussing, mean, median, and the mode will have the same value. That is called the perfectly symmetrical or perfectly normal distribution. However, the variables in our data are not symmetrical, resulting in different values of the central tendency. Here you can see the formula for this one is gamma 1 is equal to 1 by n sigma from 1 to n, means all the terms will be added. You have to find out this. That means xi minus x bar, which is the mean of the data. The cube of this, sum of the cubes of all the differences, and after that divided by this term, and that is 1 by nth of sigma from 1 to n, the summation of xi minus x bar square and whole raised to the power 3 by 2. It looks complicated, but it will show you the skewness. You have directly formula for skewness, where xi represent the value in data vector, x bar represent the mean of the data vector, n represent the total number of observation. Now let me show you the graphical representation. Here it is. There exist three types of skewness values on the basis of which asymmetry of the graph is decided. You can say this is the negative skew, then no skew, then positive skew. Here, no skew means a perfect or normal distribution is there in the data. If you can draw a line in the middle one, a perpendicular line in the middle one, you will find that data will in the form of mirror image. The first half will the mirror image of the second half. So, first case, positive skew. If the coefficient of skewness is greater than 0, remember this. If coefficient of skewness is greater than 0, then the graph is said to be positively skewed with the majority of data values less than mean. Most of the values are concentrated on the left side of the graph. So it is called the positive skewed distribution. We require library moments for the skewness function. Here is an example. Defining data vector. Here I have created a data vector. We already having that data vector in our computer. Print skewness of the distribution with the print command, and you can also print the histogram that will give you a basic idea of the distribution. So uh, here is the output of this. You can see when positively skewed, the data will be on the left side. Here the major bars are there on the left side, and lower bars are on the right side. Some data may be absent, so there will be no bars. But majority of data is here, so you can find out that the in the left side is data is concentrated. So let's do some practical on that. Here we will create the vector for this. Here is our R Studio. So I'm taking example that will directly show you this kind of distribution, and after that we will find the distribution of our samples. First we will I am creating this as x1 this time, because we are already having value inside x, so I am creating x1. You can see the x1 now having these values. You have to install first time install dot packages, then you know what is the name of that package, moments, because without installing that package you can't calculate the skewness and ketosis. So it is connecting to the site. You can see the red dot over there. It will search. And it's a very small package, so it is installed. Now I'm using the command library and then moments. Again, I'm printing the value of x1 for your convenience. And now I can use skewness. You can see this is the function which comes from the library moments of x1. I'm printing over here x1. It is positively skewed because it is greater than 0. Okay. I have taken such type of examples that will show you the positive skewed distribution. Now, let's make the histogram. Here it is. You can see the majority of the values in the positive distribution is on left side. Similarly, I'll show you an example of first on the presentation. Here it is. Zero skewness or symmetric. If the coefficient of skewness is equal to 0 or approximately close to 0, then the graph is said to be symmetric and data is normally distributed. So if you calculate the skewness that comes out to be 0 nearly 0, then the data is said to be symmetric. So what you have to do, you have to load the library moments in your computer again, then create a vector. Here I have given a command rnorm. It is a mathematical command, so you need not to go into the details, but I will tell you that it will create normal distribution. Then print the skewness of this distribution and you will find the result like this. It is nearly about 0, some bit negative, but nearly about 0. So let's create this and I will show you. Here is our R Studio, and I'll tell you that mathematical command I have used to generate random values from R. That is the R norm. Here, this time I will create this vector into x2 and I'll print x2 onto the screen, and then you can see that how many values, these are the values. It will create a normal vector with 50 values. Here mean and this is the deviation. You can see the help of R norm here. Here you can find n means how many number of terms you want to generate. This is the random data. R provides the random data function in the form of random normal data with mean equals to 0, SD equal to 1. Whatever you can give the mean and standard deviation, the value of mean and standard deviation over here. So what I have given, that I want a sample data set with 50 value, 50 elements, and mean 10 and standard deviation is also 10. So it will generate like that. Now we are already having a sample data set. We can calculate the skewness of x2. Here this time it is nearly 0, comes out nearly 0, and we'll print the histogram of that. Here we'll find this. Majority of the elements are in the middle, not in the left, not in the right. So this is a sample data set randomly created. For your data, you can calculate that. Now another example, we have seen positively skewed, then 0 skewness, and 1, this time this one. Negatively skewed. If the coefficient of skewness is less than 0, when greater than 0, it is called positively skewed. All the data lies on the left hand side. Majority of the data lies in the left hand side of the distribution. When 0, the majority of data lies in between of the middle of the distribution. and this time negatively skewed, that if the coefficient of skewness is less than 0, then the graph is said to be negatively skewed. With the majority of data values greater than mean, most of the values are concentrated on the right side of the graph. Again, this is an example that library moments defining a data vector with normal values. This time I will create normal values to show you that majority of data lies to the right side. Print skewness of the distribution with the skewness function and histogram of that. So let's do that with variable x3 onto a R console. These are just examples to show you that how this looks like in practical use. Whenever you are collecting data, you will apply skewness function and you can find out whether it is positively skewed, negatively skewed, or it is 0. This time I am creating a vector x3 to show you the example of negatively skewed distribution. Here it is x3. Skewness, then x3. You can see it is in negative but 0.5. This time it comes out to be 0.5. So in a negative, it is having the data mostly of the right side. So let's print the histogram. You can see the majority of the data is on the right side because you can see the bar at the right side is larger one. So these were the examples of positive and negatively skewed and normal skewed, zero skewed distributions. Now we are already having this X data and we can print the histogram of that. This time, what kind of distribution is this? Let's see the skewness. Then diagram is unable to show the actual values. You can use the skewness function. This time I am taking the skewness of X for my data and it comes out to be nearly 0. Minus 0.0, that means nearly 0. So it is kind of zero skewed distribution. So this is all about the skewness. We can also find out the skewness of our data set. Suppose we are having the data set here. I am having cars data set. Let's do that. Skewness of cars, then dollar, then speed. We can also print the histogram to find out what cars dollar speed is showing us on the screen. Here, it is nearly about 0. So it is zero skewed distribution where data is generally normal, not completely normal, but generally normal. A bit, you can say it is a bit negatively skewed, a bit, not completely, a bit, because you can see their bars are just a little bit on the right side. Let's check the skewness of distance. This time it is greater than 0. So we can see it is positively skewed. So histogram must be in the form of left side values. That means histogram of cars and then dollar, then distance, and you can see. Yeah, the prediction is pretty clear. Here you can see it is on the left side of the diagram. So this is all about skewness. By looking at the histogram, you can find whether it is negatively skewed, positively skewed, or it is zero skewed. And skewed, it will show you the curve of the distribution. Now let's move on to another topic. It was the output of here right distribution is having the major part. That means it is negatively skewed. The next topic is ketosis. Ketosis is a numerical method in statistics that measures the sharpness of the peak. That shows you how normal skewness shows you whether it is on the left side of the majority of the data, in the center, or in the right side of the graph. But ketosis is a numerical value that shows you sharpness of the peak of that graph. That peak of the graph, how much sharp it is. So it is defined as ketosis is the measure of the pointness of the data set, and it is defined with this. Then gamma 2, gamma 1 is skewness, here gamma 2 is the ketosis, is equal to 1 upon n sigma I to n xi minus x bar raised to the power 4. We have to take the fourth power of the differences, and we have to take the sum and find out the average of the dividing terms. Then again 1 by n sigma of 1 to n xi minus x bar whole square, and whole the term is squared. And when we divide this by this, we will get the ketosis. This is the numerical interpretation, but in R, we have very simple function ketosis to find out this, where xi represents the value of data vector, x bar represents the mean of the data vector, and n represent the total number of observations. Here, the graphical representation. Here, black curve shows you the normality of the observation. If there exists three types of kurtosis, again, like skewness, here, first one is platykurtic, that means which is near about flat. So here is the black is the peak of normal distribution. You can see it is near about, the peak is flat, near about flat. Then in mesocultic, it will show you the normal distribution as in the within this black line. The shape is normal. But in case of leptokurtic, it is too pointy. That means all the data, maximum values are in the middle of the data set. Here we find the sharpness of the peak. The ketosis is the sharpness of the peak of our data. So how to find out that? Let's do that. First one is platykurtic. If the coefficient of ketosis is less than 3, remember, skewness is measured from 0. Ketosis is measured with 3. Then the data distribution is platykurtic, means flat. Being platykurtic doesn't mean that graph is totally flat top. It may be near to flat. So again, for ketosis, we have to load the library moments. Then we have to define the data vector. And you know that repetition function, repetition of 61 and 10 times, a repetition of 64 18 times, a repetition of 65 23 times, a repetition of 67 32 times, a repetition of value 70 27 times, repetition of 73 17 times. This is, I just created a vector for calculation simply. so that we can find out there are so many values, and we will find out the plateautic data. This is an example of plateautic data. So let's do that on the R console. Here is our R console, and these are the commands I have given. This time again I'm changing my x1 for demonstration. That repeat function we studied in the first day. Repeat function, the value, and how many times you have to repeat that, and so on. Here you can see it has created a value vector x1 with these many values: 61 repetition 10 times, 64 repetition 18 times, 65 repetition 23 times, 67 32 times, and so on. So this is a random data set that I have made to show you the plateautic data. I'll use the Ketosis function here, and then x1. Here it is 2.25, and so on. Let's create histogram of this x1. Here it is. So it is not flat. This is an example to show you that near about flat, because there is not much deviation inside this data. Here, nearly flat shape. It's nearly flat, not flat. As you know the definition, it is not totally flat, but the difference is very less. So Ketosis comes out to be 2.25. So our definition less than 3. Here it is less than 3. So it is plateautic. I'll show you another example. I've taken the output of that window. So here it was the value that comes out to be from the observations, and here is the histogram of that value. Without zoom mode, you can see this is nearly about the flat, not flat, nearly about the flat. So it is less than 3. So it is plateautic. This time mesokurtic. If the coefficient of kurtosis is equal to 3 or approximately close to 3, then the data distribution is mesokurtic. The previous data you can also take the mesokurtic near about, in between these two. For normal distribution, kurtosis value is approximately equal to 3. Maximum data that will be in the form of normal distribution if the kurtosis coefficient is equal to 3 or approximately close to 3. So let's define a normal vector of 100 values, and using that we can find out this output. So let's do it onto our R console. This is a kind of normal distribution we are creating, because our norm is the creating normal vector. This time I am creating x2 again. So x2 will contain 100 values of normal vector. Here it is. Now I will find the ketosis with ketosis function, and I'll give the argument x2, which is my vector. Here it is. Every time, because at that time answer was different, this time the answer is different. Let me show you the histogram. Every time it will generate different kind of values, that's why. Yeah, you can see this is the output of histogram function. If you are having if you are doing this on your laptop, you will find that it is near about 2.27 something comes out with this, and it is an example of mesocratic because value is near about 3, not equal to 3, but near about 3. We can also generate values with 50, and find again the ketosis of this x2. This time it is near about 3 because it is 2.7 this time. So we can print the histogram of x2. This time you can see it is more clear. Third time I will generate some 20 values into x2, normal values. These are the random values because I am not having the actual data. You have to use this function on your actual data to find out the graphs and representation and values. This time it is nearly about 3, and you can see the histogram of x2 is this one. So this is all about the normal distribution or mesocratic. The shape will be perfectly near about perfectly normal. And in this, I'll show you the leptocratic. If the coefficient of ketosis is greater than 3, then the data distribution is leptocratic as and shows a sharp peak on the graph. So required for ketosis function, this is the library moments. You have to remember this. Then again define the data vector. I have used this repetition function to define this. I will take this into the account, and I will create this vector. Then I will print the ketosis with this command, and there will be the histogram with after this random repetition. You can see it is very sharp because the middle one is having highest value, all other values are lower because value is greater than 3. So let's do it and to our R console. Here again I have taken the command and I'm copying using copy paste over here. Here are the repetition of 61 for 2 times, 64 for 5 times, 65 42 times, 67 12 times, and 70 10 times. This time the value will be in the middle of the observations. So I have replaced x. Here it is. This time I will use ketosis for x, and that is 3 point something something. And if I will print the histogram of this, you already seen on the presentation, that would be like this. So you can find in this diagram that majority of the elements having the maximum value, other values are very lower. So it's a sharp peak and it is leptokurtic. Then platykurtic, mesokurtic, and leptokurtic. In case of platykurtic, the value should be less than 3. When equal to 3, it is near normal distribution. It is called mesokurtic. And in case of leptokurtic, the value is greater than 3 for ketosis. Now we will execute all these functions on our data set, that is CARE data set. So we will find the ketosis of our CARE's data set and then speed variable. What you can tell about this? What kind of ketosis is this? It is less than 3. So it is what kind of ketosis? First one, that is less than 3, and that is platykurtic. Platykurtic. Very nice. Very nice. So here we can create the histogram to see this. CARS, again $sign, then speed, and you will find that here you can see the actual explanation of platykurtic. Here you will find the plate bars in middle of the data set. This is an exact example of platykurtic. Again, we'll take the ketosis of cars, then dollar, then distance. Here one another example of this is what kind of, can you tell me? It is an example of last one, that is leptokurtic.
Leptokurtic.
Very nice. So let's create the histogram of this chart and cars, dollar, distance. Here, one thing that you can see by this diagram, the skewness is left side. That means it is positively skewed. But in case of sharpness, it is very sharp. It will call very sharp because it is greater than 3. So ketosis is leptokurtic, where we can call the skewness is positively skewed. Here I will also apply the function skewness to this variable. So we can simultaneously analyze these two with the diagram. It is greater than 0 this time, 0.7, which is greater than 0. So it is positively skewed, and you can see in the diagram also. Again, the middle value is the sharper point, having the sharpest point. So it is leptokurtic. Now, for case of speed, we can find out the skewness is negative. And also, again, I am printing the ketosis. You have both the values. It is less than 3, as we already know, and it is negatively skewed a bit. So let's print the histogram of speed. In the adjacent window, you can find out the skewness is negatively skewed. So you find these bars are a little bit, not too much negatively skewed, a bit negatively skewed, a little bit. So you can find out the bar on the right hand side a bit more. Skewness is right hand side, whereas kurtosis is near about the flat one. So you can find that the top of this chart is near about flat. So this is how we can calculate the kurtosis and skewness in the graphical manner. Let's do some more practice with all this and we'll create some data for that. So I'll show you one example that I want to import some data from my data set, and then we'll do uh, kurtosis and skewness on that data. So let's revise how to import the data. Go to the file menu, import data set, then from Excel or go to your browse menu, then go to the place where you kept your data. Here player.xls, open that data. Here it is the Excel data. It is showing me, since I am having the first row as names, so I am taking this one. Already it is having that, and default sheet data is from A1 to D10. The range is there, and I will click the import. So it is already created a vector player into my R console with read Excel command, which is the file from D drive, and you can see that data into your view menu. Here it is. Similarly, you can import your data from Excel sheet, and you can use that data. Now I am having the player data. Let's see what the headings inside this. Here age is there. It's a quantitative data. So we can perform range, mean, median, mode, all such functions. So let's find out the range first on this data, and what is the player. Okay, player dot, sorry, dollar sign, then age. Minimum age is 32 for the players and maximum age is 45. Then we can find out the variance of player dollar age. Here it is 27.06667. Then we can find out the standard deviation, which is the square root of this, square root of 27. So we'll print SD of player dollar then age. You can easily find out 5 5s are 25 and some values that will create near about 27. So by squaring this, we can find this, or by taking the square root of this, we can find this. So this is the variance, this is the standard deviation. Now, MAD of age, median absolute deviation. Then we come to skewness and ketosis. Skewness of it is negatively skewed. So majority of the data in the data set will lie to the right hand side. Similarly, we can find the kurtosis. Here we find the kurtosis is less than 3. So it is near about flat data. The data distribution is near about flat curve. So let's print the histogram to verify all these. We are using the zoom mode over here. That's why it is not showing the actual picture, but on your system you will find it out more clear. So by looking at these values, you can find out that right bars are more. The data is distributed towards right side, and which is the negatively skewed data. So skewness is negative. First thing, it is nearly about flat. There is no sharp peaks are in the data. All the data is in flat mode. So we can say this is plateautic data. I hope you can create such type of data and you can do practical on that with these functions. We can also create our own vectors in R. For example, with the C command, I am creating some random vectors. These are the random values. Argument 9 is empty. So you can see that I have left some comma here. Very intelligent. So this time I have created this data. To find out, we can use histogram. The pictorial representation will tell us something. This is the data. Here you can find out that it is sharp at some points. Another thing, majority of data is spread towards left, right. Let's see with the value of skewness and ketosis. Skewness of X. It is negatively skewed. That's why the bar is tilted towards the right side. Similarly, we can find the ketosis. It is less than 3. So we can say that bars are naturally flat. In this manner, we can find the skewness and ketosis, and we can depict it with our histogram also, which shows us the frequency and the distribution. Now, we'll find some more things that we will revise. Range of the X data. Again, you need not to find it out manually. It will automatically tell you that 12 is the minimum value, 90 is the maximum value. Then we'll find mean of all these value with mean function. Then we can find median. We are revising each and everything in this vector. So mean of X is this, median is this, and if you want to find out the mod, then you have to load the library mod est, mod estimation. You have to use MF MFP. That means of X, 32 is the mod of this data vector. Again, let me repeat because some interruptions are there on the screen. So mod, median and mean. Now let's find out the quantiles. These are 0%, 25%, 50%, 75%, 100% of our data. One more thing, summary of the X, and it will give you minimum is 12, first quartile is 37.50, median is 56, mean is 56.16, third quartile is 77, and maximum is 90.00. Again, we'll find out the med, that is mean absolute or median absolute deviation actually of X. So we can say that median absolute deviation is 32.6172 of our data set. Then we'll find out the variance of our data set, and that comes out to be 604.807. Then we'll find SD, that means standard deviation, and that comes out to be 24.59282. Again, we have minimum function to calculate the minimum of X directly. We have maximum function to calculate the maximum value directly. We also have sum function to calculate the summation of all the data in a single time. The sum of all these data items is equal to that. You can find out the mean by using this formula also, that if say I can take the variable S as sum of all X, the summation of all the data items, then we can use length function. N is equal to length. We don't know how many number of terms are there, then we can use length, L-E-N-G-T-H, length function of X. That how many values are there inside N. We can print N, this is 19. We can print sum, this is 1067. This time we can calculate the mean by dividing these two. For example, if S is the sum, we'll divide it by the total number of terms, N, it will give us this, which is directly calculated with mean function. So it is very interesting that we must know the basics, both are the same. I hope this is clear from the calculation that we can calculate with the summation, with the use of mean, we can count the number of terms, and we can find out the median also with MED function. So I hope that today's session is an interactive one, and you know how to visualize the data, how we can take the data inside the R with the import functions, and after that we can perform descriptive statistics option to find out the different values for our data set, and we can visualize the data visualization. We can also do the pie chart and all such things. Let's do it once again onto our R console with the data I have created. Let me show you. And this is, suppose we want to create the bar chart. Can anybody tell me? First, I will use box plot to show you all the quartiles. This quantiles means quartiles of the X. Here you can see it is showing me the box plot of that. I'm using bar plot to create a bar chart of X. I can also use pie chart of the X, but here you can see it is too much clumsy. We can't read the data values easily. It is showing me the values 11, 10, 9 and all such things, but it is not actually the pie chart for the purpose for which pie charts are made. Then last that we have already created, and that is again histogram. So now you know how to visualize the data. First, you know how to create the data, then how to visualize the data, how to import the data into R, how to do descriptive statistic function on the R. Okay, so for now, we end our class. Any doubts or any queries?
No, sir.
Okay. So tomorrow we'll be having another new topic, correlation in regression. That would be graphical. We will find the relation, correlation and regression between the values. That is more important. So join at sharp 6 p.m. Thank you, everyone.
Thank you, sir.
Thank you, sir.